Right, we're looking at the last section over here. We're looking at, let's go here, equations of motion. Right, when we talk about motion, remember we said you can look at it through graphs, or you can look at it in terms of equations. And we've looked at the graphs already, the three types of graphs, and I've given you a little extra bit of notes here. I gave you the position versus time graph. I gave you the velocity versus time graph and the acceleration versus time graph. And we understood that if I was looking at either of these graphs, if I was looking at a position versus time graph, I know that this 0.00 is my frame of reference. I know that a straight line here means constant velocity. All right, I know from my velocity time graph, if I have positive slopes, if I have a positive slope or an upward slope, then I have a positive acceleration. A downward slope, I have a negative acceleration. And I know what the acceleration versus time, it's a stepping kind of graph. So I know that the area, the slope of a position versus time graph is going to give me velocity. I know the slope of a velocity time graph is going to give me acceleration. I know the area of a velocity time graph is going to give me the distance or the displacement. And the acceleration time graph, the area is going to give me the change in velocity. And then from there, I can work out the actual velocity. So when I'm looking at this section, please make sure you take this diagram down. I'm not looking at just the motion of something in terms of a graph. We want to look at describing motion in terms of solving problems. You're looking at situations where I have to do calculations. And in order to do those calculations, I've got to look at something called equations of motion. Now with equations of motion, right, and we work with equations of motion, we have to look at actual equations of motion. So at this point in time, we have looked at certain types of variables, right? And when we talk about variables, these are the type of variables that we've looked at so far. We've looked at something called the initial velocity, and I know that the SI units for that is meters per second, right? And this will always be at t0. So it's the original velocity. We also looked at v final, which is the velocity at time. This can be any time, please make notes, after 0. Another vector quantity we looked at is displacement, delta x, and that's measured in meters. We looked at time, which is a scalar that was measured in seconds. We also looked at time interval t, which is measured in seconds. And I know that when I see delta, when I see this delta, it means change, right? Time interval means the final time minus the initial time. Please make sure you get that in. Right, we looked at acceleration. From acceleration, we also had a different formula, and we can still use that. That acceleration is the change in velocity over the change in time. So I'm looking at v final minus v initial. And you can see that all of that is over some sort of time period. So not only can I use these graphs, I can also use these different variables. So the types of variables we're going to be looking at are right in front of us here. You have to know these variables. You have to know their definitions. You have to know what they look like. But most importantly, you need to know, what do they mean, right? And how do I use them? So what's going to happen in these types of calculations, and you'll see that as we go on, is that we're going to do calculations based and use these variables in our equations. Now, not all textbooks are the same and textbooks differ. So there are alternative symbols that we can use. For example, if I'm using VI, I know that's the initial velocity. But in other formulas in different types of textbooks, they might use, let's have a look here, I'm just pasting it in, U, the letter U. But just remember, it's the same thing. I'll just zoom in a little bit so that it's not. Right? It's the exact same thing. They've just used, instead of using VI, they're using a U. Instead of using VF, they're using a V. And instead of using displacement as delta X, they're going to use S. So it depends what type of textbook you're using. But both of these types of variables, vector variables, are relevant for our calculations. All right, let's have a look. Once you've got all of this down, please make sure you take this down, you highlight it because it's important. Once you've got all of this down, let's have a look at the actual equations. So here we have equations of motion. All right. Now, when we have these equations of motion, you will find the equations of motion in your formula sheet, which is at the back of your book. Have a look at your formula sheet, and what you should find in this section of motion is something that looks like this. There are 4 equations in total that we look at. All right. These are the equations. You are not required to know the equations, but you are required to work with it. So when we're working with these formulas, the first thing that you need to understand, let's have a look at the first one. The first one says VF is equal to VI plus AT squared, AT, which is final velocity is equal to the initial velocity plus the acceleration multiplied by time. The second one is delta X is equal to VI plus VF over 2 times time. So displacement is equal to the initial velocity plus the final velocity all over 2 multiplied by time. The next one, equation number 3, delta X is equal to VI times T plus half AT squared, which is delta X is equal to the initial velocity times the time plus half times acceleration multiplied by time squared. And the last one is VF squared is equal to VI squared plus 2A delta X, which is the final velocity squared is equal to the initial velocity squared plus 2 times acceleration times displacement. So when I'm looking at each of these equations, I can use any of them to solve for any other variable that I don't know. But the important thing that you need to know here is you may only have one unknown variable. Right? If you have more than one unknown variable, you're going to have to use simultaneous equation. So the questions can vary a lot, but the following method for answering them will always work. So we use this when we're attempting the questions that involve motion with constant acceleration. You need to know these quantities and be able to calculate them. So in each of these, something missing. So if I look at the first one, I'll notice that there is no delta X value. So that means if I'm ever looking for delta X or I don't have delta X, then it's best to use this formula. If I look at the second one, the delta X one, over 2, you'll notice in this one, there's no acceleration. All right, there's no acceleration value. So if you're doing any calculations and you don't require acceleration, it's best to use that sort of formula. The next one that you're looking at, number 3, you'll notice that there's no V final. There's no V final variable, so you don't have to worry about putting v final into that. You can't use it if you are looking for v final. So know which formulas are missing something, so it means you can't use them. And then in the last one, there's no time, right? And that means that for that calculation, if you don't have the time information, you can use any of these. We'll see when we do a few examples now how it looks. Another way that we can see these types of formulas, or they can be presented to us in a different way, using, let's say, these ones up here, the U, the V, and the S. So sometimes you could see equations of motion, and they give it to you in a different format. And that format we can see over here. Again, you may only have one unknown variable, but if I look here, can you see that I've got a V here, and I know that that V stands for final velocity. And I've got an S here, and I know that that S is going to be displacement. And I've got a U somewhere here. There we go. I've got a U, and that's going to be initial velocity. But can you see this? The equations are the same. So if I have a look over here, I can see that the equations from here are the same equations from here. So 1 and 1 look the same. I still got V final is equal to V initial multiplied by acceleration times time. Also, don't forget, we mustn't, because it's still a vector. It's a different name. So over here, I should have a line there. I should have a line there. Here, over here. It's still the same. These are still all vector quantities. That does not change. So please make sure that when you're writing these things down, you make sure that you write them with the vector signs. There wasn't any vector signs when I found this image. All right, so those are the different types of equations of motion, and we're going to look at how to go through a question. What are the rules? What are the things you have to do? And then we're going to look at some problems and see how we could solve those things. All right, so let's have a look here. We're looking at motion in one dimension, and we're looking at problem solving. So when we have these types of questions, you'll find that you can sometimes be stressed. Right? You can get confused. It can be overwhelming. Right? And all in all, you could do the one thing that I see most often. You can say, I went blank. Right. Now we can afford the I went blank thing. The reason for that is in motion in one dimension, you are given certain bits of information. And the bits of information that you are given can help you answer a question. So there are a couple of things that we need to look at. The first thing is you have the formulas. They will be given, right, on the formula sheet. The formulas are given to you. The second thing you're going to get a question. And that question is going to come in the form of something we call problem sums. Or problem situations, rather. Right? And we remember this from primary school, because there's all this information that comes in a form of a paragraph or sentences, and you got to break it down into a calculation. So after you read your problem sum, you are going to ask for a calculation. Right? And in your calculation, you're going to need to find something. Right? But also in your question, in your problem sum, they are going to give you information. So we need to find a method so that we don't go blank in an exam. So we need to look at how am I going to do this? So this process that we're going to use it throughout the course. And when we mean course, I mean it has to be used in grade 10, it must be used in grade 11, and we're going to be using it in grade 12. So we've discussed this a little bit. I want to go into a little bit more detail. All right, so let's look at the following steps. It says construct an informative diagram of the physical situation. So you can either draw You can sit and think about it a little bit, or you can do a bit of a diagram as rough work, right? Just an idea of the physical situation. Visualize what is going on, right? The second thing says identify the list of the given. Please make sure you're getting this information into your book of the given information. This is important. This information here, when we talk about the given information, that's going to come from the question. So everything that you see in the question, you need to make sure you write it down. And it says here we must write it in the variable form. So let's just go here quickly. So what we mean by the variable form is we need to write down all of our information. So I'm going to say, for example, VF is this and VI is this, and they gave me delta X and they gave me time. So you need to write down all the given information. After that, you must write down the unknown information, right? So our standard list is VI, VF, delta X, we've got time, we've got change in time, we've got acceleration, we've got change in velocity. So I've got all of this information. Now when I'm doing the unknown information, I can only one unknown at a time. There must only be one unknown. If there's two unknowns, there must be two calculations. Every formula that we have can only have one unknown situation. So please make a note of that. All right, the next thing we're looking at here, it says, identify and list the equation that will be used. All right, remember, it's the one of the unknown. So remember what I said. I said you need to look at which formula has no time, or it has no V final, or it has no delta X, or no whatever else, right? That is the formula. So you need to be able to identify and list the equation. So in this step here, we must choose the equation based on all the information that I have. So I'll need to know my known information and I need to know my unknown information in order to do this. All right, the next one says substitute known values into the equation and use appropriate algebraic steps to solve for unknown information. All right, when we have these types of questions, I want you to think of them because they're equations. We can solve for the unknown. You know, in maths, when they say solve for x, that's what we do here. That's the kind of mathematical skills. We need to get the unknown by itself. We need to solve for it. The last thing says check your answers and ensure that the answer is reasonable and mathematically correct. Reasonable means it makes sense. For example, I would never have a car traveling at 16,000 meters per second. That is just not possible. Because realistically speaking, if I had 28 meters per second, then from 28 meters per second, then I'm looking at about 100 kilometers per hour. Right? Around that idea. So be realistic. A bullet, for example, will never be traveling at 2 meters per second. That is just not realistic because bullets should be traveling at that speed. So please make sure that your answers are reasonable. Right? Mathematically correct, it means no negative answers. No negative answers. You must make it positive. And remember, if it's a vector, then it must have magnitude plus direction. All right. Another thing that we can look at when we do something like this is we need to look at different types of conversions. Oops. Conversions. Right. We need to make sure that we're working in the right variables. Right. So I'm just going to put up a conversion table quickly. Right. There are two types of conversions that we need to look at. The first type of conversion is if they give me my answer in kilometers per hour, I know that the answer has to be in meters per second. So if I want to go from kilometers per hour to meters per second, I've got to go divide by 3.6. And from meters per second to kilometers per hour, which they could ask me my question like that, let's multiply that value by 3.6. Also notice that sometimes the format we're going to use is m.s to the power of negative 1 or km.h to the power of negative 1. It's just a negative exponent because sometimes you're going to see textbooks or worksheets giving it to you as m per s. All that means is m over s or km over h. And I know that to find speed, I've got to put distance over time. That's all that it is. Right, so what we do is we bring the exponent to the top, and mathematically that h will end up with an exponent of negative 1, not 1. So those are just the different ways that it can come across to you, but don't panic or freak out. It's fine, just the way it is. Right, the other one that you're going to have to do is meters and kilometers. You'll notice that I've put here the word correct across the system that we're going to be using. So for speed, I'm just going to put here, this is for speed or velocity. And then the bottom one here is for distance or displacement. Those are important conversions that you have to do. Please make sure that these conversions, when you do them, all conversions must be done. If it's not in the answer, all conversions must be done at step 2. Right, it must be done early. Please don't wait to start with the calculation, then start doing things like that. It's not going to work out for you. So these are your two very, very important conversions that we're going to be looking at. And the next thing we're going to be doing is some examples. So I'm going to do a couple of examples with you, and then after that, you're going to work by yourself independently. All right, the next thing we're looking at is some problem solving. So the first thing you would have noticed here is that when I do my problems or I do these problem solving questions, I kind of keep my formulas with me, right in front of me. That's why I have a formula sheet. I keep the formula sheet in front of me so that I have all of that information there with me, because you have that in the exam, you need to use it to your advantage. All right, let's have a look here. The first question says, we're starting with problem number 1. Problem number 1 says the runner accelerates 4.2 meters per second squared for 10 seconds before winning the race. How far did he or she run? Right. The first thing that we said that you need to do is you need to draw some sort of picture. All right, so let's have a look. Accelerates for 10 seconds. So let's say that's the finish line. And here I have Jonas. And Jonas is running and running and running, and he's running towards the finish line. And this whole process, from where he is to the end, that took 10 seconds. And what he did was he accelerated at 4.2 meters per second squared. Oops. Right. Now we want to know how far did he or she run. So we've got Jonas, he's a boy. And let's add what we know. I've got acceleration, which is 4.2 meters per second squared. Right. I've got time, which is 10 seconds. Right. And in this whole thing over here, I don't have anything else. I want to know how far. I want to know delta x. Right, that's a problem. Let's have a look at how we solve that. Right, and then the last bit of information and how we're going to see this is a weird one. It says he or she accelerates 2. So he initially, the speed was not that amount. He had to come from somewhere. Now, if you think of a race and how races work, the other bit of information, we know the V initial, which should have been, if you're starting a race, 0 meters per second, because you shouldn't be moving. But when you start a race, when you start here, when it started, this was V initial equal to 0 meters per second. And you kept speeding up and accelerated to that amount. So what we've done here is, I've got my given information, but can you see how you need to be able to read the question? If you don't read the question, you're going to have a problem. So we need a formula that has acceleration. So of all of these formulas, I can't use formula 2. I need a formula that has time. So I've got 3 other formulas. I need a formula that has delta x. I can't use formula number 1. So now I'm left with the last 2, 3 and 4. And I need something that has V initial, right? But no V final, because that we don't know either. So look here between the 2, and I can't use 4. So let's see what I'm left with. I'm left with a formula, so now I need to select my formula. I can say that delta x is equal to V initial multiplied by time plus half of the acceleration multiplied by time squared. So now I've got to substitute. Once I chose my formula, I need to substitute. So delta x is equal to V initial, which was 0, multiplied by the time, which is 10 seconds, plus half multiplied by acceleration, which is 4.2, multiplied by 10. And that's what I've got so far. All right, so let's have a look at it. If we simplify that a little bit, I know I've got delta x here is equal to 0 times 10 is going to be 0 plus half times 4.2 times 10 squared. Put that into your calculator. And that's going to give me 210. So then delta x is therefore equal to 210 meters. And because it's a vector and they've given me no directions, the direction of motion. Right? And that's your final answer. Marks 1, 2, 3, 4. Please note that if you have an answer without SI units and the direction for this section, it will be marked as incorrect. So please make sure you don't have answers that look like that. And let's have a look at the next question. And let's have a look here. We've got the next question, problem 2. Please make sure you're writing these questions down. You don't have to write the formulas out each time because you'll have the formulas in front of you. But you do need to make sure that the formulas are on this page so that you have them right there as we're going through all of these. Right, problem 2. It says a plane starts from rest and accelerates uniformly over a time of 20 seconds for a distance of 300 meters. So we have an aeroplane. Oops. Let's just say this is our aeroplane. There, right. Got this aeroplane. Right, and it's accelerating from rest. So when it starts at the initial thing, we have V initial, which is 0 meters per second. So read the question. And it accelerates uniformly over time. So the acceleration is constant. All right. Then it says for a time period of 20 seconds. Time is 20 seconds for a distance of 300 meters. So let's see what I've got here. I've got V initial at 0 meters per second because it was at rest. I've got time here, which is at 20 seconds. I've got delta x here, which is equal to 300 meters. I've got V final, which I don't know. They want the plane's acceleration, but acceleration, which I don't know. So in this thing, the known values are here. That's what I know. What I'm looking for here is the unknown. And this VF here, that I just don't know. So let's look at which formulas I can use. So I need a formula that has V initial, time, and delta x. So anything that doesn't have time has to be scratched out. So I can't use equation number 4. Right, the next thing I don't have V final. So any formulas that have V final, I'm going to take those out too, because I don't have that. And I'm left with the last one, which is delta x is equal to V initial multiplied by time plus half a t squared. My V initial, I know, is 0. My time is 20 seconds plus half. My acceleration, I don't know. And then time, they're telling me that time is 20 seconds. 20 squared. Alright, so if I have to do something like that, and my distance here, is 300. Alright, so that's the kind of setup that I have. So now what I'm left with is, I'm left with a situation. So I can put this here into the calculator. A half times 20 squared. And that's going to give me 300 is equal to 200A. Now I want that A by itself. So I'm just going to go up here. I must take both sides and divide it by 200 to get rid of that. That means acceleration is then equal to 300 divided by 200 should be 1.5. And for acceleration, it's meters per second squared. And because it's a positive value, then I can say in the direction of motion. Right. So when we're working with these kinds of questions, you'll notice that when you get your final answer, you'll be able to write down the distance. But can you see, I've got a diagram, I'm writing down my information, choosing a formula, I'm substituting, I'm solving, I'm making sure that my acceleration, my answers make sense. Now let's have a look at the next question. Alright, let's have a look at this question. It says a ball free falls, right? When I see free fall, anything that free falls is only affected by gravity. And what did we say about gravity? If something's affected by gravity, it has a constant acceleration, a g we can call it, of 9.8 meters per second. And what direction does gravity fall in? It's in the, if it's going down, I can say that it is positive, right? From the top of the roof for 5 seconds, right? So I got that information. Then it says, how far did it fall? So that's talking about distance. And what's its final velocity at the end of the 5 seconds? So here's where things get a little bit more tricky. So graphically, if I had to draw this, let's say that's a building. And I had a ball here. And this ball has to fall down, right? Well, normally when we do these equations, and I want you to think about it like this. The reason why we use delta x, remember we spoke about it. If I'm using delta x, it means I'm moving in the x direction. So if I had a Cartesian plane, when I'm moving horizontally, I move in the x direction. But if I'm moving this way, I'm moving in the y direction, right? So that's what we mean by x direction, y direction, because things are going to change a little bit here. So let's have a look at what we mean by that. Let's write down our information. So it says a ball free falls from the top of a roof, all right? That means that when it falls, before it falls, the V initial value is 0 meters per second. It's not moving, it's going to still fall, right? The delta Y value, because now we're not working, the ball's not traveling this way, right? The ball is traveling this way. So we're looking at delta Y. So wherever I see delta X in the formulas, I can now convert it to delta, oops. Whenever I see delta X, I can make it delta Y because it's going up and down. The delta Y value, the distance, the displacement in the Y direction, that's up or down. So remember, delta Y is vertical, which means, oops, vertical, which is either up or down. We don't know that value. We know that the acceleration, because it's a free fall, it means the acceleration is 9.8 meters per second. Right. We know that time is equal to 5 seconds. And they also want to know VF. Now, when we talk about VF, right, this is a strange one. When we talk about VF, if this ball is going to fall, and let's say it's going to hit the ground, we know that when it hits the ground here, it should be 0 meters per second because it's hitting the ground. It's going to stop moving. What they want you to find is this value. Just before it hits the ground is V final. So when we talk V final, it is the velocity just before the end, right? In these types of questions. So not at the ground, just before that. How fast is it going just before it hits the ground? Right, so let's look at all of this. I need two calculations because there's two questions. The one question needs delta Y. So I need any of these formulas. Remember, this is going to become delta Y. This little thing over here is delta Y. Over here, this is now becoming delta Y. So I need a formula that works with V initial, right? I have time and acceleration, but I don't have V final yet. So I can't use this one. I can't use that one. I can't use this one. So I'm going to use the one that I've been using. Except now when we write it out, we have to write it a little bit differently. So we're going to do two calculations. So let's say for the first calculation, I'm going to say delta Y is equal to V initial multiplied by time plus half acceleration times time squared. All right, so when I'm looking at this situation, let's put in my information. My delta Y, I don't know. My V initial, I know, was 0, multiplied by my time, which was 5 seconds, plus half. Now, this ball is falling down, so it's a positive value. If it was going up, it would be a negative value. So we're going to use positive plus 9.8, positive 9.8, multiplied by time, which is 5 squared. All right, so delta Y is then equal to, what's half of 9.8 times 5 squared? I pop that into your calculator and you should get 122.5 meters. Now we do know what's the direction. Downwards. Or you can say down. Right. So now you have a bit more information. We can go up here and we can say that this is equal to 122.5 meters. Great. Now we need to do a second calculation. The second calculation wants V final. So I need a formula that has V final, that has acceleration. So V final, acceleration, V initial, and I can use delta Y, and I can use time. So I need to find that sort of formula. So if I look at all of my formulas, I need any formula that has V final in it. So I have formula, I'll do it in a different color. I've got the first formula, I've got the second formula I can use, or I can use the last formula, right? But here's the kicker about all of this. Can you see here? We found delta y. Now this is a two-part question. And by finding this delta y, we could have made an error. And if we use this error to do this calculation, then everything is incorrect. Right? You may get part marks, but everything's incorrect. So we need to find a formula that avoids using delta y. Because if I made a mistake here and I take the mistake there, I'm going to lose all of the marks. So let's look at which formulas don't. So if I look at formula number 4, I can't use it. If I look at formula 3, I know I'm not using it. Formula 2 has delta x there. I can't use it. So the only formula I'm left with is VF. I've got your VF is equal to VI plus AT. All right, so let's put that information. So I've got VF is equal to VI, which I know is 0, plus acceleration, which is positive 9.8, multiplied by time, which was 5 seconds. And in that thing, 9.8 times 5 is going to give me my V final is equal to 49 meters per second, because it's velocity, downwards. No? Let's say if the answer is positive, so downwards, because that's how it was moving. Or you can even say in the direction of motion. Right? And that's your final answer. So in essence here, you've got such a simple statement. Can you see the type of calculation that we have to do? So it's not as simple as it looks. You have to do the work. You have to draw the diagram. You have to write down your information. You have to understand what is going on. If I'm working in the y direction, if I'm working in the x direction, those things are very, very important. So look at the next question, problem 4. All right, problem 4. It says a bobsled team accelerates the sled to go 150 meters per second. 150 meters per second in 3 seconds from rest. Let's look at A. What is the sled's acceleration and what is the distance the bobsled? So I'll do that. What is the distance that the bobsled team traveled? So there's 2 types of bobsleds. One, you can go by yourself. This is the 2010 Olympics picture of what a bobsled looks like. You can either go by yourself or you can go with your team. And in this one, we've got a team. And our team, have a look now, looks like this. So we've got our team here. Let's get that out of the way. We've got our little bobsled team here. And let's look at what they're saying. They're saying about our bobsled team is that it goes to 150 meters per second, right? Which means its final velocity is equal to 150 meters per second. It's very, very fast, like very fast, right? Because this surface is almost frictionless, so it is possible. And the time it takes them is 3 seconds. Let's fasten the car. From rest, which means the V initial value that it starts off with, let's do this like this. So over here, the V initial is equal to 0 meters per second. And this whole thing, what we said, was taking us that time there of 3 seconds. And when it got to the end, it had a final velocity of 150 seconds. So 2 questions. A wants to know what's the acceleration. So I don't know my acceleration value. And B wants to know what's my distance. In other words, they want the delta x value of the situation. So you have to do two calculations. For the first calculation, we need final velocity, time, initial velocity, and acceleration. So look, I've got final velocity, initial velocity, acceleration, and I've got time. So already I can see I can use equation number one. So I'm going to use equation number one for A. I'm going to say A is equal to V final, is equal to V initial plus acceleration times time. So my V final was 150 meters, stay in here, is equal to V initial, which is 0, plus acceleration here, we don't know, and time, which is 3 seconds. All right, so all I'm left with then is 150 is equal to 3A. Divide both sides here. I'm just moving up. Divide both sides by 3. That cancels out. And A is equal to 150 meters per second squared in the direction of motion. Right, so that's the first one. The next question they're asking for, I need to just change these colors, is they want the displacement. All right, so I need a formula that uses, because now I know this value is not 150, sorry, I made a mistake. 150, divided by 3, is 50 meters per second squared. Sorry about that. So I know that this value is 50 meters per second squared. All right, I need a formula that uses V final, V initial, right? Acceleration, time. So the best formula for me to use, and let's have a look here. What's important to us is if I can find a formula to use that doesn't have acceleration in it, because that's unreliable right now, because what if that answer was wrong? I need to find a formula that doesn't use acceleration. So the best formula for me, it has delta x, it has V initial, it has V final, and it has time. So I'm going to say for B, delta x is equal to V initial plus V final all over 2 multiplied by time. So that's what I'm using for this one, which is, I think, equation 2. So I don't know my delta x value. I know my V initial was 0. I know my V final was 150. I know that my time was 3 seconds. So I can just put all of that into my calculator. And I'm going to get 150 divided by 2 times 3. So that's going to give me 225 meters in the direction of motion. So again, to reiterate that, if your answers are ever positive, it must be in the direction. Please don't take shortcuts. It's in the direction of motion. If your answers are ever negative, then we must change to positive. And we must say in the opposite direction of motion. Alright, so let's just remember that. So there we go. I've answered A's question and I've answered B's question, and those are my final answers. And let's have a look at the next question, or next problem rather. Alright, problem 5. With problem 5, it says here, a bullet leaves a rifle with a velocity of 450 meters per second, 452 meters per second. While accelerating through the barrel of a rifle, the bullet moves a distance of 0.93 meters. Determine the acceleration of the bullet. Right. So remember what we said, we must make sure we draw an image. So let's just look at what we mean by the barrel. So I've got myself a gun here. Right, there's my gun. And the barrel is between here and here. So in that zone, what do I know? I know it leaves the rifle. So when it exits there, it's got a velocity V final of 452 meters per second. So when it leaves there, so the bullet's going to come out and it's going to leave at that final velocity. Because remember, it starts off here in this case, and then it travels up and it moves. I also know that in this barrel, this distance that it's moving, I know that the delta x value there is equal to 0.93 meters. Very small, 93 meters. Very small little space, right? I know of that information that because the bullet starts off there in the cartridge, I know that the V initial of the bullet is 0 meters per second. And they want A, acceleration. So now I've got to look at a formula that has V final, V initial, delta x, and acceleration. So I can't use this one because it has time. So anyone with time has got to go. Right, then I've got 2. This one's also got to go. There we go. So I'm left with the 4th one. Right, so I've got here my formula. So there's my known information and my unknown there. So I've got V final squared is equal to V initial squared plus 2 acceleration times delta x. Right, so I know my VF is 452 all squared is equal to the V initial, which is 0 squared, plus 2 times acceleration, I don't know, times 0.93, which is my displacement. So I've got now 452 squared is equal to 2 times 0.93, which is 1.86 A. So what I have to do first is, the best thing for me to do is I've got to get rid of that squared, isn't it? Right, so I can square root both sides. That will cancel. So I've got 452 is equal to the square root of 1.86, which is equal to 1.36, 331817A. Now I need to get the A by itself. So I'm going to divide both sides by 1.363. Can you see I'm not rounding off? I'm keeping it at 1.36318. I'm keeping it at that. So then I've got A is equal to 331.42 meters per second squared. And there's your answer. And remember, in the direction of motion, or you can say in the barrel. Right? So that would be how you would answer that kind of a question. So that was a bit of a hectic one, but have a look here at how high that acceleration is. It's a bullet coming out of a gun or inside of the gun before it even leaves the gun. So you need to make sure that when you have an answer, what we meant by make sure that it's reasonable, it makes sense, and that you are mathematically correct. The reasonable part is because it's a bullet, it should be moving very, 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 very fast. So please make sure that you understand that concept. Let's look at problem 6. Problem 6 says, the observation deck of the Empire State Building is 381 meters above the street. Determine the time required for a penny to fall from the deck to the street below. So the first thing we need to do is we need to look at that as an example of a building. The Empire State Building is quite tall, and we've got our observation deck, and that's the ground there. Right, so we're saying that this distance, now have a look again, this distance to this distance is in the y direction, which is delta y, which is equal to 381 meters. Right, they want the penny to fall, and they want the time that it's going to take. All right, we don't know that. But we do know about this is that it's going to free fall. Now, if something free falls, it's only affected by gravity. So, the acceleration value we have here is 9.8 meters per second. The symbol we use for gravitational acceleration, let me just put it here, is G, which is equal to 9.8 meters per second. And this thing is falling down. So if it's falling down, the value must be positive. If it's going up, the value must be negative. All right, any other information that we know? We know that when you're going to drop the penny up here, your V initial must be 0 meters per second. And we don't know V final. All right, so let's look for a formula that uses V initial, delta y, because remember all of these x's are now going to all become delta y. So it must have delta y. It cannot have V final. So any formulas with V final, we have to take it out. Can't be this one. Can't be that one. Can't be this one. All right, so the one I have left is number 3. So I've got delta y is equal to V initial multiplied by time plus half times the acceleration times time squared. All right, let's look at how that's going to look. Delta y we know is 381, which is equal to V initial, which is 0, multiplied by the time, which we don't know, plus half. All right, acceleration must be positive 9.8 t squared. All right, so that's a weird one. All right, the first thing, this is 381 is equal to 0 times time is still 0. So I'm left with half times 9.8. And half times 9.8 should be 4.9 t squared. So the first thing I need to do is get this variable by itself. So I'm going to divide both sides by 4.9. So I'm going to take 381 divided by 4.9, which is going to give me t squared, that cancels, is equal to 77.75510.204. All right, but I don't want t squared. I just want time. So I need to square root this whole thing. So I take all of that and square root it. That square root is going to cancel that square, so I'm left with t over there. And all of this needs to be square rooted. So I'm going to end up with 8.82 seconds. And because it's a scalar quantity, I don't have to worry about writing in the direction of motion. I just know that, therefore, it will take a penny 8.82 seconds to fall from the top of the Empire State Building. All right, so that makes sense. All right, let's have a look at problem 7. All right, let's have a look at problem 7. It says a bowling ball is dropped on Jupiter from a height of 3 meters with an initial velocity of 0.4 meters per second. Let's look here. Some informations. Bowling ball. Oops, undo that. Bowling ball. Jupiter, height of 3 meters. There we know some sort of information. And an initial velocity of 4 meters per second. The acceleration of gravity on Jupiter is 24.5 meters per second squared. How long does it take for the bowling ball to reach the surface of Jupiter? Right, let's have a look at that, what we mean by that. So let's say I have this planetary body, say Jupiter. Okay, that's what it looks like, right? And what happens is, 3 meters above the surface, so from here to here, that displacement is up and down. So it's a delta y, which is 3 meters. And what's being dropped at the top there is a bowling ball. All right, so this bowling ball is going to be dropped and it needs to come down. Now we know about gravity. Gravity is down is positive value. So it's dropped from 3 meters, which is that distance over there, with an initial velocity. So when it starts, V initial is 0.4 meters per second, like that. Now every planet, this is important, every planet, including the sun, has its own gravitational field. And if it has its own field, it has its own gravitational acceleration. Now I know for Earth, it's equal to, G is equal to 9.8 meters per second squared. But I know for other planets, let's say for Jupiter, this time, G, they've given you at 24.5 meters per second. All right, so the A value that we have, or your acceleration now, is a different value. All right, let's see what information we do have. So let's look at this given information. We've got delta y, because it's going up and down at 3 meters. We've got V initial at 0.4 meters per second. We've got acceleration now at 24.5 meters per second. Oops. Meters per second squared. Sorry, I must change that to 2. And how long? All right. Long means time. So that's what they want to know. V final, I don't know. And I don't have also. So I need any formulas that don't use V final. So let's have a look. I can't use this one. I can't use the first one. I can't use this last one. So now I'm left with number 3 here. Alright, so let's have a look at that. I know that delta y is equal to, remember all the delta x's, because like I said before, you've got a y-axis, you've got an x-axis. If you're moving in this direction, right, you got, so let's say east and west, you're working in the x direction, your displacement is in the x direction. If you're working here like north to south or up and down, you're working in the y direction. So delta y is equal to V initial, right, oops, times time plus half acceleration times squared. All right, so in this one it's a little bit different. All right, we've got delta y here at 3 is equal to V initial, which is 0.4, multiplied by time plus half. Acceleration is at 24.5 t squared. All right, so what you need to do is you need to sort out this sort of equation. All right, so let's have a look at how we're going to sort this out. All right, the best thing to do, Because I've got an equals to sign here, I'm going to make everything equal to 0. So what I've got now is I've got 3 minus 0.4t plus half times 24.5 is actually equal to 12.25. 12.25 t squared is all equal to, or not plus rather. Remember, I'm taking everything, taking all of this here, so the signs are going to change. It's plus here, it's going to be minus. Minus, what's it? What did I say? 12.25 t squared is equal to 0. Alright, so what I have here is I've got myself a quadratic equation. So let me rearrange it. It's negative 12.25 t squared minus 0.4 t plus 3 is equal to 0. But I don't like the negative, so I'm going to multiply everything by negative 1. So I've got 12.25 t squared plus 0.4 t minus 3 is all equal to 0. And what I need to solve for is I need to solve for t. Right, this is where things get not complicated, but a little bit different. I know that my quadratic equation is ax squared plus bx plus c. Now, when I factorize it, I need to put it into 2 brackets. And from there, I can factorize it and find the value of whatever my unknown is. But sometimes that's not possible because if I have a look here, I've got decimals. So if I use this as my base formula, we can substitute. We can say x is equal to b, negative b, plus minus the square root of b squared minus 4ac and all of that over 2a. Right, now where am I getting all of that from? I'm getting it from this base formula. So if I want to substitute a, I need the coefficient. Okay, let's just do this with another color. For a, I need the coefficient of a squared, of x squared. For b's value, I need the coefficient of x. And if I want c's value, I need the constant. So in the formula that this is to factorize decimals. All right, when it's not possible to factorize in an easy way. It's a cheat that we can use in physical science and maybe in maths in later grades. So I'm going to say x is equal to, whoops. All right, so the x that we have here is actually t, time. We need time and we don't know that. So in my formula, a is equal to 12.25, b is equal to 0.4, and c is equal to negative 3. So don't forget a couple of things. You need the signs. All right, let's have a look here how this is going to look. So I've got t is equal to, because it's not x, we're solving for is t, negative b, negative 0.4 plus minus. Now plus minus, because remember when we have these brackets over here, we can either have positive values or we can have negative values. So this plus minus here, you're going to have to do this question twice. Once you're going to have to do it with a positive, and once you're going to have to do it with a negative. So let's have a look. Positive over b squared. So b is 0.4 squared. Look at how I'm putting the brackets. Minus 4 times a. What's a here? 12.25. Multiplied by c, which is negative 3. And all of that over 2a. Oops. 2 and a was 12.25. Right. Now when you put it into your calculator, when you put, I'm just going to make this a bit smaller so I can work. When you put in a positive over there, you're going to get one kind of answer. And when you put in a negative, you're going to get another answer. So when I put in a positive, when I say negative 0.4 plus all of this over 2a, I'm going to end up with an answer of 0.4788143734. And when I put in the negative, I'm going to get an answer of negative 0.5114674346. Right? Now, if I'm looking at those two answers, what do I know about time? Time is scalar. So here it will be t is equal to positive t is equal to, this is going to be negative t is equal to. Time is a scalar. Right. And that means it only moves in one direction. So I can never have negative time. So I cannot use this as an answer, the negative answer. I have to have a positive answer. So therefore, the time it will take is equal to 0.48 seconds. And that's how you would answer a question like this. Don't forget also, another little tip. Here, remember what we said, if something falls down, right? Something falls down, we're going to take that value as positive. And if I look here, it says it's dropped to the surface. So if you look here, this value here was positive 24.5. If it was thrown upwards, then I'd have to use a negative value, which I'm not using for this question. So it's another thing that I remember. So your calculation for this question should look something like this. So this here is a big NB. It's a way of factorizing without having to put it into two brackets. You're still going to get a value for x or for value for t, but we're going to use this formula. And this formula is called the quadratic equation. So this is what we call a higher order question. This is as difficult as it will get. Right? So let's just remember here, when we use a negative sign, you got negative t is equal to this. But you can't use it because time is a scalar, and that means there's no negative values allowed. So it's quite complicated, but you should be able to work through it. And all you do, remember with this here, is put into calculator. The biggest problem people have is they forget all of their brackets, or they forget this little bit, or they forget to square here. But you need to make sure you put it properly into this equation. You will not be given this equation in an exam. You have to memorize it. And remember, because it's called the quadratic equation, it works with the quadratic function or the quadratic standard formula. Now we're going to do one more example, and then we're done, and then you're going to have to go and do an exercise by yourself. All right, this is the last problem that I'm going to go through with you. Obviously, if you need help after you watch this video, I will help you. We have some time. So please come and speak to me if you're having any issues. This is just me working through problems with you so that you can see how you use these formulas, how you choose these formulas. What do I actually have to do to get through this work? These problems look simple. Okay? One sentence. What could go wrong? And you would have noticed by now, things can go wrong. So you need to make sure that you actually participating in these types of questions. Right, problem 8. It says the truck accelerates uniformly from rest to a speed of 9.2 meters per second. It then says over a distance of 26.2 meters, they want the acceleration. Right, let's have a look at what information we actually have here. Right, so I've got a truck. Okay, got a truck. This is my 18-wheeler truck, or whatever the case is. got my truck over here, and it's accelerating uniformly. So it means it's continuously speeding up, which means it started somewhere with a v initial value of 0 meters per second. But that we also know that because it says from rest to a speed of 9.2. So they've said it started there and it ended up with a v final value of 9.2 meters per second. And this whole distance that it's taken, oops, undo that. The distance that it took to do this whole thing was 26.2 meters. That's where we're at. All right. So I also know my delta x value. They want to know the acceleration. So what I don't know is acceleration, but I also don't know time. But my main thing I don't know is acceleration. So I need a formula that has v initial, v final, delta x acceleration, but it doesn't have time. So I need to eliminate those equations. So first I'm going to take out this one. Doesn't have, it has time. That has time. This has time. So I'm now left with the last equation, equation number 4. Just put that in. I've got vf squared, oops, is equal to vi squared plus 2 times delta a times delta x. All right. My vf was 9.2 squared is equal to vi squared, which is 0 squared, plus 2 times acceleration, which I don't know, and my distance was 26.2 meters. All right, so all I have here is I've got 9.2 squared, right, which is 84.64. 84.64 is equal to 2 times 26.2 is equal to 52.4 a. But I need a by itself. So I'm going to divide both sides by 52.4. That's going to cancel. 52.4. I need 86.64 divided by 52.4. And the acceleration is going to be equal to 1.6 meters per second squared in the direction of motion. And that's how I get to the end there. So remember with marks, let me just show you how marks work. You get a mark for your formula. You sometimes get 2 marks for substitution. You can even get a mark for that substitution. You then get a mark for your final answer. You sometimes get 2 marks here. You could sometimes get 3 marks for substitution. But you need to understand that you need to have a formula. You need to substitute. You need an answer with magnitude, the SI unit, and the direction. So make a note for yourself how important this is. So if you notice now how I do this, I follow the same rules. I draw a picture. I write down my given information. I write down all of my unknowns. Right? I figure out what is the correct equation that I need to use. I substitute into that equation. I've got my answer plus direction for vectors. Right? So make sure you use this system. Use it. You've got a set of rules. Make sure you utilize that set of rules so that you don't fall short when you do these types of questions. So once you get to the end of this, that's that. When we get to class tomorrow or whenever you've done this, the next teaching day, I'm going to give you guys an exercise to do. So all the best with this. Please make sure that you've got all of the notes, all of the examples, everything in your books. All right, I'll see you guys at school.